Hello everyone, welcome to video 5.4. This is on exponents and scientific notation. So let's get started. So a power or an exponent, we have a to the b power here, and it is the product of b factors of a. So if we have, say, a to the second, that's a times a. So you can see we have two factors of a. A to the fourth would be 4a's being multiplied together, and so on and so on. As multiplication is repeated addition, exponents are repeated multiplication. Now, if we have repeated exponents, then that just becomes more exponents. So there's a lot of rules around exponents that we could get into in this section that we're really going to not get into. So we're just going to kind of scratch the surface a little bit of what exponents are. And we're talking more about exponents as a concept of repeated multiplication rather than as sort of an idea onto themselves. In fact, it's really only one property of exponents that we're going to talk about in this section. So there's a lot with exponents that we're sort of going to gloss over at this point, but that's okay. Like I said, we're talking about this mostly as an extension of the idea of multiplication. Now, we've seen this idea already in some sense when we've talked about powers of 10 and place value at the very, very beginning. So even if we didn't write hundreds as 10 to the second power or thousands as 10 to the third power, we still have this idea there. So the notation might be a little bit new for some students, but this idea has already been there. So it's really the developing a notation for an idea that's already been brought forward, hopefully in class. I also want to point out that, for some of you, you might be thinking that, you're going to be teaching kindergarten, first or second grade, where students may not be seeing an awful lot of this. But part of the reason why you take a class like this is so you know what math is ahead. First off, you might end up moving grade levels anyway. So this might not be something that you're teaching right away, but it might be something that you're teaching down the road, or maybe even the next year. You may student teach at one grade level, and then in your first classroom could be a different grade level where you are going to be teaching this. But even if this isn't a topic that you're going to be directly teaching, knowing how this works allows you to set the stage developmentally for some of these ideas. And so talking about multiplication as repeated addition, or even talking about groups of groups of groups, these ideas sort of chain together and form, like, structurally, the path toward exponentiation. So, there's a lot of merit in doing these things, even if you think you may not be teaching them right away. So I mentioned we're only really going to look at one property of exponents, and it's this one property. What do we do about a to the 0 power? Does that equal a 1 or does that equal a 0? And we're going to look at this really in two different ways. So we'll look at it in terms of a pattern, but we'll also look at it in terms of the actual rigorous property itself. So let me divide this down here. So in terms of the pattern, so let's look at, say, powers of 2. So 2 to the fourth power is going to be 16, 2 to the third power is going to be 8, 2 to the second power is going to be 4, 2 to the first power is going to be 2. And so just as we talked about before, we can see the exponent is decreasing by 1 each time. And then we can see that the solution is dividing by 2 each time. So if we carry this forward one more time, then we would get 2 to the 0, and then 2 divided by 2 leaves a 1, not a 0. So students like to think this is going to equal 0. I think it kind of makes sense. You got a 0 here, you got a 0 here. I mean, why wouldn't 0 make a 0? It makes perfect sense. But hopefully you can see that that doesn't work because we're dividing this thing down. And if we divide a non-zero by a non-zero, we can't possibly get a 0. The only way we're going to get a 0 when we're dividing is if we start off with the 0. Hopefully you know that we can't divide by 0, but we'll come to that here in the next chapter when we start talking more about division. So by pattern, we can kind of see that this 2 to the 0 equals 1. And we can extend this out. We can generalize it. We can generalize it using, this is not just a property of 2. A to the 4th is a product of 4 A's. A to the 3rd is 3 A's. And you can see we've divided by A here. And so this same idea applies. A to the 1st is just A, and we're dividing by A until we get to A to the 0, and then A divided by A equals 1. So we can generalize this as, to show that it's not just a property of 2, it's any number that we want to use. So we can show this by pattern. And then likewise, we can show this in a little bit more rigorous way. Now, we would need to introduce this property that A to the K over A to the M is A to the K minus M. So this is the division property of exponents. And so when I divide two exponents or two numbers with exponents and they have the same base, this number here that is being raised to the power is called the base. So this is we have a common base here. So if I had, say, 2 to the 3rd over 3 to the 5th, this wouldn't work because the bases are different. But if the bases are the same, we can subtract the numerator exponent minus, and then subtract the denominator exponent from that. Now, if we know this property, then this A to the 0 becomes relatively simple to show because we just take A to the K over A to the K. We just make the exponents the same. And so then this would be the difference of those exponents, which is A to the 0, but then anything over itself is 1. So this shows that A to the 0 equals 1. It's a little bit more rigorous. It's also a heck of a lot quicker. You can see the idea is really the same because what we're really using is this idea that this is going to be the case where we have something divided by itself. And that's really what we had here with 2 divided by 2, and it's what we had here with A divided by A. So the idea isn't really any different. It's the means by which we show it. We can do it the pattern way, which doesn't involve introducing this property, but takes a little bit longer and maybe isn't as rigorous. And we have this way using the properties, which is definitely more rigorous, but almost certainly more complicated, more complex. We have to introduce a new idea in order to get there. So, one of these two methods should work. It might be worth your while to show both. Some students will latch on to one certainly quicker and better than the other. So it's worthwhile knowing both of these. Okay, we should introduce this idea of scientific notation. Scientific notation is going to be used whenever we're dealing with very large or very small numbers. Now, these are relatively subjective terms, and for some students, 200 may seem like a very large number, and to a certain extent it is. I'm not going to discount that. But we're talking about numbers that if we were to write them out in their literal form, it would be very inconvenient or very unwieldy. And I know those are two also very subjective terms. I mean, inconvenient and unwieldy, depends on the person. But we're talking about things usually past maybe 9 or 12 place values long, especially when there's a lot of zeros to that number. And if there's not a lot of zeros to the number, if there's a lot of non-zero digits in the place values, then there's typically some rounding that goes along with this to make it a little bit smaller of a number. So let's look at the form, and then we'll look at some examples of this. So we have this part A, which has a name. It's called the significand, if you're curious, or the more popular name probably is the mantissa. It's not a name you hear an awful lot. So I'll also write significand. Yeah, I wouldn't bother too much with this, but just know that it has a name. All right, so there is a name for that. And then we have the order of magnitude B over here. A has a restriction that it's between 1 and 10. Now, it can be equal to 1, but it can't be equal to 10. Because if it could be equal to 10, we would just increase the order of magnitude by 1 and make it equal to 1. So we don't need both the 1 and the 10. And this keeps it to where it's one place value integer, a decimal point, and then whatever decimal stuff sort of comes after that. So it keeps it as in the form of something point, something decimal. And then our b is going to be some integer value. Now it could be positive, it could be negative. And if b is a positive, then we know we're dealing with a large number. So if b is greater than 0, then we know we're dealing with a large number. And if b is less than 0, it's a negative, which means we're dealing with a much smaller number. So let's look at a couple of examples of this, and we'll see how this works. So we've got I've got here the mass of the Earth is 5.972 times 10 to the 24th kilograms. Now, I'm not sure where I found this. I found it somewhere online. I'm sure I Googled it, and it came up from somewhere. One of the things that's worth having a conversation with your students about is whether or not this is an exact value or an approximate value. And pretty clearly this is approximate. And so there's some error to this. There's some rounding error to this. But the point is that we don't want to write this fully large number, even if we could tell what it was. This may be an approximate based on the method by which it was found, not because we know the exact value and then approximated it. So there's a lot of error in finding this number, and whether that's at the beginning, middle, or the end of finding this value, it could be all three, depending. So what does this number really look like if we were to write all of this out? Well, this 10 to the 24th is going to tell us this order of magnitude. And so one way to think about this is this 972. So if we were times 10 to the first, then we know we would just multiply it by 10, which would move this decimal place one spot to the right. If it were times 10 to the second, then we would multiply the 5.972 by 100, and it would move 2 times. And so by looking at these smaller values, we start to notice this pattern that whatever my value of b is, that's going to determine how many decimal places we're going to move. And in this case, because we know b is greater than 0, it's a positive value. We know this value is going to get larger, so it's going to move to the right. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Just barely got in there. So we put in a 0, we put all of these zeros, and this gives us an idea of what this looks like as a literal number. Now, I wouldn't do this a whole bunch of times for reasons that should be obvious, but it's worth doing one time so you get a sense of how big this number is. And we can put some decimal points, or not decimal points, but some commas in here to mark off these 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And try to see if anybody wants, any students want to try to figure out what this number would be, the actual name. Millions, billions, trillions, quadrillions, quintillions, sextillions, septillions. So this would be 5 septillion, 972 sextillion kilograms. Yeah. So we can see this is a number you wouldn't want to write an awful lot. You certainly wouldn't want to do calculations with this number. So we see the merits of why this is a much better way of writing this number. Again, writing this thing out, not something you need to do a whole bunch of times, but it's worth doing at least once so students can see the basis of comparison, why this is more convenient. We can do the same thing with a smaller number. So the diameter of a hair is between 17 and 181 millionths of a meter. So now this is a little bit different because now we have the number not in scientific notation form, and we want to put it into that form. So we've got 181 millionths. So we know it's 181 divided by a million. Now we have to be really kind of careful because there's a lot of places to make mistakes with decimals here. We can convert this denominator into 10 to the sixth, right? And so then this is 181 times 10 to the negative 6. So when this denominator moves up here, it becomes a negative. So a to the negative k is the same as 1 over a to the k, another exponent property that we're not really getting into quite so much in this chapter, but does exist. And so now we could use this as an equivalence, but it's not a scientific notation form because our a is too big. And so we have to move this decimal point over and make it 1.81. And so now what does that do to the 10 to the negative 6? So as this gets divided by 10, this has to get multiplied by 10. And so this would actually be 1.81 times 10 to the negative fourth. And one way that we could show that would be to do some equivalent fractions here. This is the same as 18.1, so we've divided this by 10, so we divide this by 10. So this would be 10 to the fifth, and then that also equals 1.81 over 10 to the fourth. And so when we convert that over, that becomes 10 to the negative fourth. So there's a lot of ways to go wrong. Like I said, there's a lot of sort of moving parts with these exponents. This is a arrow, not an equals or an 11. There's a lot of places to go wrong with this. And so thinking about different ways of, we can do all of this without using this exponent property if we're thoughtful and mindful about how we're going to approach this problem. We could also see here that this millionths, if we were to do this negative 4, this decimal place is going to move to the left 4 spots. So we do 1.81. This is going to move 1, 2, 3, 4. And so another really easy mistake to make with this is to think that to the negative fourth is going to involve 4 zeros. And that's not the case because the first spot is always going to be moving past this non-zero. So for negative fourth, we know we're going to have 4 minus 1 because we're not going to count this first spot. So non-zero, 0, 0, 0. So we're going to have a decimal point, 3 zeros, and then 181. And if we count these places off, we can see tenths, hundredths, thousands, tenths, hundreds, thousands, 10,000s, 100,000s, millions. And so we can see our million spot right here. So the 181, so we read that to the smallest place. That last, the smallest place value in the 181 would be in the millionths place. So we can work this problem in both directions. Again, there's a lot of sort of, I won't say trickiness. There's a lot of places to go wrong. There's a lot of moving parts to this, and you have to be very, very careful in how you count these things out. So if you're going to be doing examples with this with your class, if you're not entirely comfortable with scientific notation, with your place values, with exponents, with any of these things, you really want to make sure that you work out your examples and you're not trying to work these things off the top of your head. I would say even if you are pretty good with this sort of thing, you want to work out your examples and not be doing a lot of this off the top of your head. So there we go, scientific notation. So for your checkpoint, I want you to think about this figure here. The Earth is approximately 92.96 million miles from the sun. So I want you to write that distance in scientific notation. What do you think that would look like? Now, I will give you a little hint. Notice that the decimal point is kind of not where we want it to be for scientific notation. So it's going to have to move. And so when you move that decimal point, what is that going to do to your exponent on your 10? Is it going to make it bigger or is it going to make it smaller? So you know it's going to adjust by one, right? But does it make it one bigger? Does it make it one smaller? So I'll leave you with this problem. As always, if you have any questions about this problem or anything else from this chapter, by all means, please bring it to class or bring it to office hours, and we'll get them answered. All right. Thank you.